The what?
Automatic capture.
Do they work?
Yeah. Just as long as you raise cattle. Yeah. It's fantastic.
But they're accurate.
I'm not confident these exact.
It's a brand new marker.
Awesome.
I take this back. I got it right from the cabinet. I don't know how new it is, but it stinks. This is the second one I got. Oh, this one's better, okay. All right, questions about any of the homework, any questions?
Could you do 4.64?
4.6, okay. Give me the,
So it says there's a 1 millimeter air gap in a toroid with a mean radius of,
hold on, this is a toroid, right? Not a solid, okay.
and it says it has a mean radius of 50 centimeters and a cross-sectional area of 2 centimeters squared.
Okay.
U relative of 6,000 and 4 amps is being driven through 30 loops.
4 amps, did you say?
Yeah, 4 amps, 30 loops, and it's asking to determine the magnetic force of pulling the gap closed.
All right, the whole deal is I'm gonna turn this into an equivalent magnetic circuit that parallels the similarities to an electric circuit you'll recognize. All right, we developed this. This is called magnetomotive force, is parallel to the voltage, which is an electromotive force, and so forth. So for this thing, what you actually have is I almost think that somebody does this on purpose as a joke. We'll work with that. Anyway, what it amounts to is you're going to have an equivalent magnetomotive source, like a voltage source. Hello? Sometimes don't ask me. I get the weirdest calls sometimes. They want me to help me pay off my college loan. All right, y'all follow me? That's like a voltage source. Now the equivalent magnetic reluctance right here is going to have 2 parts. All right, the first part is going to have to do with the actual bar itself. And that has to do with the length around that toroid over the cross-sectional area of the toroid divided by mu relative mu naught of the toroid. And I think everybody understands that. The next has to do with the gap. This is the reluctance of the gap. That has to do with the length of the gap divided by mu naught divided by the cross-sectional area. So that's really the trick right here in terms of how to set up the equivalent circuit for this. After that, we'll get to these values in a second. The next thing you do is find out the equivalent magnetic current, which is simply going to be Ni divided by the sum of these reluctances. I'll call this reluctance of the toroid, reluctance of the gap. Now, I'm putting it all up here before I put numbers in. Y'all follow me on this? It's just checking boxes. After that, we know this magnetic flux is in Webers. We can get the B field everywhere in this system because one thing we recognize about this since this is likened to current and this is a series circuit, the magnetic flux is the same everywhere. Y'all follow me on this, class? It's just like that. So the magnetic flux density, which is the B field, will be the same everywhere, including the gap. So that's just going to be the total magnetic flux here divided by the actual area, cross-sectional area of the gap right there. And we'll get to that in a second. Everybody follow? Now, once you have that, you can get the H field that's like the E field everywhere. Do y'all follow me? And we can say that in the gap, right here, the H field in the gap would simply be B field in the gap divided by the mu of the gap, which is mu zero. Do y'all agree with that, class? It's just mu zero, correct, everyone? So that's going to be magnetic flux over mu naught A of the gap, which is the same thing. I'm assuming that there's no difference in the cross-sectional area in the gap, it's small, and the actual toroid. You all with me? Now once you have that, the magnetic force, and I put this down here, that would be pulling this together. All right, so the magnetic force itself would be equal, it's always proportional to the cross-sectional area. And then what you'll see is it's going to be equal to 1/2, and you'll see mu naught times H in the gap squared in there. And the reason it's not 2 there is because this gap's singular. Do y'all follow me on this, class? There's not 2. Now, can everybody follow me what I'm doing? Who asked this question again? The solution should be up for that one too, right? Is Whitmer's solution following this outline, or did he do it?
Yeah, for the most part. He's saying that the force is just mu naught H squared A. He doesn't have a 1/2.
Oh,
but
he's going to have this. I'm sorry, mu naught H squared A. All right, go ahead. I'm sorry, you're right. Go ahead.
yeah, I mean that's all he has, and then he just calculates that out and finds the force is equal to 1.6 newtons.
Now, the reason, I almost don't want to spend much time on this, but I'm just going to say this. Magnetic force anywhere has got to be proportional to cross-sectional area. And then the force per meter will be this. Now, here's the thing. This force is pulling these two together. And here's a general concept. Please try to grasp this. The basic way a magnetic force always works is to increase or decrease the reluctance of the actual system that the flux is flowing in. In other words, like the resistance. Well, if this gap goes away, there is no reluctance of the gap, right? That's what it would like to do, so it's pulling it towards each other. Y'all follow me? Now, when you have a bar magnet, remember when we had that, and you don't have to write this down, but when we had this type of a thing, and we had gaps there, and remember this is a high reluctance material right here, then this gap here and this gap here would be the majority of the reluctance in this circuit, magnetic circuit, if this was made of steel. Do y'all follow me on this? And it would pull the thing up. That's the way it works. What it has to do is a minimal energy principle. And remember with force, the way Whitmer does it, he says force times dl is actually equal to the change in energy of the system. And the minimal energy principle is they want to actually say this in a way that's correct. It wants to cause the total energy in the system and the gap itself to be a minimum, which would shut the gap. I'm not saying this is quite the way I'd like to say it, but this is the way you do this problem in a nutshell. Now, I don't hold people accountable that much for any kind of magnetic force stuff, because that's sort of the way you would actually do a lot of these things would be from a basic physics point, and then you work from there. The way we're doing it is in a very general sense. All right. Do you want me to work all the numbers on this one?
No,
I mean, the numbers are pretty straight. The only thing you have to get is this length, the length right there of the of the toroid, and the length of the toroid is just gonna be 2 pi times the mean radius of the toroid, 2 pi r. And then after that, everything falls apart. Okay. I'm trying to find something I can parallel this to. You know how when you had, back in the day when you had physics and you had the spring problem, you know, the spring was at rest here. When you compress the spring is gaining potential energy, right? If there was a gap here as you're moving, right, that would be moving through, then, or moving from that rest point, if you're exerting a force on that to crunch it down, it's gaining potential energy, and what it would like to do, if allowed to, it would like to extend itself the complete distance to minimize the amount of potential energy being held by the spring. That's the idea. It's the same idea here, only I'm trying to convey this in a way, and it's hard for me to draw a parallel right now, but anyway, that's how that problem would be done. Other questions? Let me think about that and come back on this one. Anything else? Okay. I want to do one or two things. There's a lot of interesting things we can talk about. But these are sort of the classic kind of things that you should know as electrical engineers. Now, we talked about just having a conductor moving through space. You all remember that? If we had an actual loop, please listen to this. Suppose we had a loop like this, and the area of the loop was A, okay? And there was a magnetic field in here. Now, let's say the magnetic field's coming out of the board. But it's everywhere. It's everywhere. And this magnetic field is not going to be a function of position. So it's going to be some function of position, function of, say, x, y, and z, as some scalar value b naught. And it'll be, and I'll put a coordinate system on here. Call it out of the board x, that direction y, up z. And I'll say that this thing is in the AZ direction. So the magnetic field's coming out of the board. This loop's in the plane of the board, and it's moving in this direction at velocity v. Now here, I've got the entire loop moving. Y'all follow me? And I want to know what the VEMF is right here. So that's what I'm after. Well, the way you would do a problem like this probably would be the easiest is this. You would say that the VEMF, the induced force right there, or induced voltage, electromagnetic force, or the voltage would be minus ddt of the integral of B dot ds over that surface area of the loop. So then you would put minus ddt, and here, remember I got this equation right here, right? So then, you almost need some coordinate systems to start with. If you say the axis is right here, the z-axis at the point at t equals 0, this is where the loop is. So this is the position at t equals 0, the loop is on z-axis. And then it starts moving. Do y'all follow me? Can y'all follow me? I'm saying right now it's on the z-axis. It's got some dimensions. And maybe I better be clear here. Let's say this has a width w and a height h. And I'm saying the thing's moving in that direction. Y'all follow me on this? So now, if you take a look at this edge of the loop would have a coordinate y right here, as it's moving out, y would be equal to it's simply gonna be equal to vt, right? The velocity t, because it's going in the y direction. Y'all follow me? That would be this coordinate. Give me any given time. It's 0, this edge is right here, right? As t increases, it moves further and further away, correct, class? So, when I do this thing, and I put the limits on, the height will always be from 0 to h. But now, when we take a look at the limit in the horizontal direction, in the y direction, it would be from vt to vt plus the width. Y'all follow me in this? Because this has a width w. Y'all follow me? So that's we have to integrate over that surface. The surface is moving. You with me? All right. Then we put down the B field, which is some B naught f of x, y, and z. We don't know what that is yet. It's stated in the AZ direction, and it's dotted with the differential surface right here. Well, this differential surface will have to have dz, dy value. And it will be in the AX direction. You know, I did something wrong here. This would have to be in the X direction to be proper, because I have X coming out of the board. So this should be an X here. So now when I take a look at this, I have minus ddt of, and I can go from 0 to h and do that. Boy, I didn't put this down. It should be d, in this case dy dz, in the ax direction, because that would be the differential surface. You can see the ax's are going to dot out. So now I have minus ddt. It's an integral from 0 to h. I'll do that integral right now. These will dot out to 1. When we integrate dz, we just get an h here. So h times b naught. And then you've got the integral of f of x, y, and z dy from v of t, vt to vt plus the width w. And you would have to, as this could be a function, we don't know what the function is, of position, you'd have to do that integration before you could actually take the time derivative of that. But I'm showing this for a reason, because a classic problem that occurs all the time, and that you will see, is this. And this was one, I think, a homework problem I gave you to. You will have a current I, doesn't have to be time varying, and you'll have a loop like this. And this loop will be moving at some velocity v, and they'll want to know what the voltage is here, the EMF, as a function of time. Y'all follow me on that? Now, if you think about this, this is exactly what I just showed you, right? Listen to me now. You're going to see this problem. Can you get, first we need the B field inside this loop. Can we get that? Yeah, right. We know that positionally what it is, right? If I tell you it's moving at that velocity and say at t equals 0, it's 1 meter away, can you write an equation for this edge? Sure. What would you say? If at t equals 0, it's 1 meter away, you can call this rho for all I care about. You could say rho, this position right here of t, would be 1 plus v t. I might as well call v naught t, so it's constant. Y'all with me? Now, if this had a width w, you could say the integration, therefore, that we would do would go from that point, right, rho naught of t, to rho naught of t plus w. Do you all agree with that? Then you would have to integrate over the height, which is just multiplying it by h, right? Correct, class? Then after that, you do the integral and then you take the time derivative of it, right? Now here's one thing I'm gonna tell you that'll simplify your seeing this. If you look at this, and instead of actually doing that, you can do that, but instead of doing that, you see how there are 4 members here, 4 straight members. Please listen to this. Now, I know that the induced electric force is always gonna be what? V cross B. It's like the electric field that's caused by motional EMF, right? By motion, correct, class? All right, now look at this. B's into the board, right? The B field's into the board. Here I have V cross B. V cross B, y'all follow? V's going that way, cross B. That would be an electric field in this direction. Do you all agree with that? What about over here? What's the direction of the electric field? Still V cross B is still this way, right? You see how these 2 electric fields would develop voltages across the in there, right? What about the voltage developed on the lower part?
0.
It's 0, and why? Because V cross B is in this direction. You all see that? Well, the path integral of E dot dl, if this is perpendicular to the path, the contribution of that over this member would be 0 and this member 0. You all with me? So what you would actually do if you wanted to break it down, make it simple. You could say this problem really boils down to figuring out the voltage difference between the top and bottom of the first rod, call it VEMF1, and then you've got the voltage difference between the top and bottom of the rod here, VEMF2, right? Y'all follow me? I'm only looking at the edges now. I'm not looking at this part and this part. Well, these 2 are moving, they're displaced. So this voltage right here, we can get by doing V cross B, correct, class? We can do the voltage here, V cross B, correct? And then we know that these top members just short them out. We would take this voltage minus this voltage to find the net voltage that's going to be driving current in that direction. Does this make sense, what I'm saying? How many see this right here? Do you not see it back there? Or? I'm just making sure you all see it. Now this is a simpler way to do it. The big trick on all this thing is getting the positions here and here as functions of time. Because remember, V cross B, what you really are finding is the actual velocity that you need to, well, the position and the velocity. Actually, I'm sorry, just the B field. You need the position to get the B field. That's the key thing for this one. And you can solve it. Y'all follow me on this one? Do you remember this is a homework problem? I don't know which one it is, but this is classic. Did Whitworth do it this way, or did he do it with take the integral of B dot ds and then the time derivative? Do you remember? Anybody look at that one?
He didn't take the time derivative, he just did the closed interval of U cross B times the differential length.
We had a time, interval. We did a time-based one, but it was the current line was time varying.
Yeah, that's a loop is stationary.
Yeah.
Yeah.
Under a velocity on the loop.
I think there is one, I forgot which one it is, but I know it's in there.
We have one that we had a single rod with a velocity on it, not a loop.
Yeah, it's just a single.
Yeah, this is like 2 rods.
Yeah. I don't see it.
But there should be a single rod. Yeah, I'm sorry, that's figure 5, problem 513 is just a single rod.
Yeah, that's what I see.
So you would have 2 rods and you'd have to subtract the voltage from the outer one to get it. But that's a classic problem. And just understand how to do that. Out of curiosity, if we're going to do this, I'm going to say I is equal to 10 amps, and here it is in a nutshell. 1 meter width, 1 meter height, moving at a velocity of 20 meters per second outward, and at t equals 0, the displacement here is 1 meter, and I'll call this direction just rho. So rho is equal to 1 meter at t equals 0. So loops here at t equals 0. Find the induced voltage here. All right. Y'all follow me? Here's the way I'm going to do it. I'm not going to do the integral on this one because the B field is exactly predicted, right, as simply I times mu 0, over 2 pi rho in the A phi direction if we use cylindrical. Y'all with me on that, class? Assuming this is the z-axis right here. Okay. I'll break it down into 2 segments. The first segment I'm going to get the voltage on. First, I'm going to get the induced E field here. The induced E field on the first section is V cross B. And that would mean the voltage, V EMF1, would be equal to EI times the height. Since it's a meter, it's just EI times 1. Y'all follow me on this? I'm trying to just isolate this first portion right here. Okay, now we know the velocity, right? The trick is getting B as a function of time, is it? So, by the way, let's go ahead and just get the right direction of the actual induced voltage. So, if it's moving that way, you all agree the B field's into the board? So the voltage is up, right? It's going to be positive, therefore we can say V EMF 1 is equal to V cross B, or we know it's going to be in the upward direction already. So it's going to be V is 20. We don't even need to bother with the cross product. Here, B is into the board, it's I mu 0 over 2 pi, and now we need rho as a function of time. Do y'all follow me? Right? Rho is in this equation, I need that as a function of time, correct? This VEMF is going to be velocity is 20, it's really up here, yeah, I showed it. It's the induced voltage EI is the velocity cross B because they're orthogonal. We already got the direction V is given as 20 meters per second. This is that. So what's B going to be? Just take a look. What is an equation for this point? Rho of t would be equal to 1, right? Y'all with me? Plus what? Plus 20t. Yeah, I gave you velocity is 20, right? Y'all agree with this, class? Can y'all see? All right. So I just put one down here. I put 1 plus 20t. Right? That's VMF1. And what would VMF2 be for the outside one? Or the one here? Class? Same exact dimensions except for what? Same exact statement except one. What is it?
2.
That was a 2 down here, right? So EMF2 would be equal to 20 times mu naught I over 2 pi, and then it would be 2 plus 20t. And then the net voltage driving current this way. So the net voltage, you might say, in that loop, in this loop, driving current this way, not that potential. You all follow me? It's the actual voltage, because this is the voltage from here to here. That's the actual polarity. You all follow me? It's positive, and this is the greater voltage. Do you agree with me there? So the net voltage that would be driving current this way, and I'm just gonna call it the VEMF, and I'll call it a prime, that would be equal to this minus that, and so it would be 20 mu naught I over 2 pi. And then what I would do is this, I'd take the first part, 1 over 20 t plus 1 minus the second part, 1 over 20 t plus 2, and that would be the net voltage going this way. Do y'all see this driving current around in the clockwise direction? Because this is the dominant voltage, right? Now hear me. That means this polarity voltage here would be the negative of that voltage, the prime voltage. Do y'all see that, class? Just think about this. The actual voltage I have, if you put the connecting lines here and here, the net voltage is trying to drive current this way, isn't it? So if I broke this here, this voltage would actually be negative. You follow me? All right. That's sort of in a nutshell one thing I wanted to make sure I settled. Now, I'm going to mention one other thing today when you get your quiz, and it's something, and it's really a concept that you understand pretty darn well because you're electrical engineers and you've had circuits. It's something called displacement current density. Y'all remember hearing about displacement current from when you were in physics or not?
Yeah.
All right, really the best way I can explain this is it's based on measurements, and it's explained in this way. Normally, if you have curl of H, you have J, all right? J is real current. It's real electrons that are moving, or real charge that's moving through space, unbound. Y'all follow me? If you somehow could spray paint electrons and watch them at a conducting wire with a resistor and a battery, you could see them circulating. Y'all follow me? They move. That's what's associated with this current density. It's called conduction current density. But there's also one other kind of current, and it's called displacement current density. That's this. Now, the reason I'm making a point about this, Dr. Whitmer's book does, but here's why it's important. You know, if you just had a battery like such, and you put a capacitor here, assume it's been that way for a very long time, there's no current that flows if that's a truly an ideal capacitor, right? The only thing that happens is there's charge developed here. Everybody agree with that? So there's no real current that can flow through this if it's been there a long time. Do y'all agree? Okay, now, if I take this and I replace it with something that's time varying, some V naught, say cosine of omega naught t, then I know what? I do get a current, don't I? Y'all follow me? That's called a displacement current, right? We can figure out what that current is. This would be I'll just call it I C of t. That's actually to the value of C times the time rate of change of the voltage across it, C dV dt, right? Now, is there any real charge that moves through this region? But what is it doing? There's an electrostatic repulsion or attraction that's causing charge to either build up or leave the top and bottom plate, right? And that charge is something that causes current to flow, but no real current moves through there. The way we explain that phenomena is with something called displacement current in there. And displacement current would be this term macroscopically. Microscopically, it's this. It's just d dt. Y'all with me? Now, the reason I say it's microscopically, if this is the current flowing through there, and there's a cross-sectional area A, then I could say the displacement current density in that capacitor would be this, IC of T, divided by the cross-sectional area A. Do y'all follow me? Just take the current density divided, current divided by area. It's gotta be the current density, right? Well, that current density has nothing to do with real charge moving. It's called the displacement current density. And in fact, this would be equal to the partial of B with respect to T. I'm not gonna prove that today, but it is absolutely true. So that's what this term is in Maxwell's equations. I wanna mention one thing about this right here. It's a very straightforward thing to solve these type, if they ask you something, any kind of a problem, finding both J and D, if you have E, are trivial, because J is sigma E, right? And D is simply what? Epsilon E, right? So taking a derivative of that is no problem. Okay, I'll give you your quiz now. I covered what I needed.